Magnetic field due to electric current.
Welcome student. Today we have to find out the force between the two parallel conductor through which current is flow. For that, first of you we know that when the current is flowing through the conductor, suppose their current is I, then at distance D. Suppose this will be the distance A. Now this will be the point is suppose there P. At point P, how much amount of magnetic field is produced? We have already obtained the equation and their values is what we get there? B, which is equal to the mu 0 I upon simply 2 pi D. So this much amount of magnetic field is produced at point P due to the current flowing through the conductor. Right? Here we want to use this equation for the next part. Right? Then when we want to find out the force between the two long parallel conductors or wires, so for that here we get the two different cases. First one is here the current is flowing through both the conductors which are maybe parallel or it may be anti-parallel. Right? So that is also called as the like current and unlike current. So here we want to find out the equation of force for the like current. Like current. Here, like current means, first of here, we want to take these two conductors. Suppose this will be the first conductor and now this will be the second conductor. Right? Here, the length of both the conductors are there, suppose L. And again, both the conductors which is placed at the distance is there, suppose D. Here, the distance between these two conductors are there D. And again, both the conductors are parallels to each other. Suppose here, if we consider I1 amount of current is a flow through the first conductor and I2 amount of current is a flow through the second conductor. This will be the first conductor and now this will be the second conductor. Here, like current means here the direction of flow of current through both the conductors are there same. It means that direction of flow of current is same. That is called as the like current. Then, now here we want to write down the equation for the second conductor. For second conductor. See here, through the first conductor, I1 amount of current is flow. And we know that if the current is flowing through the conductor, then near the conductor, how much amount of magnetic field is produced? Just we have already seen that equation. Then when the current is flowing through the first conductor, then at distance D, it means that at the place of the second conductor, there the magnetic field is. So B1 which is equal to the, what we get there? Simply mu 0 I1. Now this will be the magnetic field is produced due to the current is I1. So that's why mu 0 I1 upon simply 2 pi D. Right? Suppose this will be the equation number 1. It means that this conductor through which I1 amount of current is flow. So this current at the place of the second conductor, this much amount of magnetic field is produced. And now through the second conductor, I2 amount of current is flow. So what we get here? We get the current I2 and again this conductor which is placed in the magnetic field of first one. Then how much amount of force is act on the second conductor. Now the force on the second conductor, that is F2, which is equal to the, what we get there? Simply here the equation of force is ILB sin theta. What we get there? ILB sin theta. Here instead of small l, here we want to take the capital L. Capital L represents the length of the conductor, and here the length of the conductor is L. Then here, now this is the direction of flow of current, and at the distance d, the magnetic field produced by the first conductor, that is the current I1, their direction is, see here, if we use the right hand thumb rule, then what we get here? Here, so this will be the outstretched thumb indicates the direction of flow of current. Then the direction of magnetic field is this curve one, right? It means that, see here, here the direction of magnetic field is, now this will be the magnetic field produced by the conductor 1. Again this will be the magnetic field produced by the first conductor. Again here. Then for this one is y. Right? It means that this will be the direction of magnetic field produced by the current I1. Then at distance d, the direction of magnetic field is this one. Right? It means that along this direction. So this will be the direction of magnetic field, that is B1. Then here, suppose here if we consider this will be the direction of magnetic field B1, and now this will be the direction of flow of current, then the force acting on the second conductor is here. For that here we want to use the Fleming's left hand rule. See here. First of here in left hand rule, what we get there? First finger of a left hand which indicates the direction of magnetic field. Then second finger, that is the middle finger, represents the direction of flow of current. Then outstretched thumb indicates the direction of force acting on that conductor. Then see here. Now this finger represents the direction of magnetic field, right? Then middle finger indicates the direction of, what we get there? Direction of their flow of current. Then here outstretched thumb indicates the direction of force acting on the second conductor. It means that this will be the direction of the force which is acting on the second conductor. That is the force acting on a second conductor by the first one. That is the magnetic field produced by the first conductor. So that's, so this will be the F21. Right? Simply F2, or if you take there F21, meaning is the same. But here the angle between the L and B is 90 degree. Now this will be the direction of length, and now this will be the direction of B. So the angle between them is there 90. So that's what we get there. Here theta which is equal to the, but theta which is equal to the 90, then sin 90 which is equal to the 1. So what we get there? The force acting on the second conductor F2 which is equal to the simply ILB. But for the second conductor, the value of current is there simply I2. Their magnetic field is there B1 and length is as it is. But now here we know the value of B1, this one. So we want to substitute these values in this equation. But before that, suppose here this will be the equation number 2. Now we want to substitute the equation 1 in equation 2. So what to get there? Therefore F2 which is equal to the I2 is as it is, again L which is also as it is, but the value of B1 is, what to get there? Mu 0 I1 upon simply 2 pi d. Right? Now again we want to rearranging that. So F2 which is equal to the mu 0 I1 I2 again L upon 2 pi d. Right? Now this will be the equation number 3. It means that this much amount of magnetic force which is acting on the second conductor by the magnetic field produced by the first conductor. Right? Now this is about the second conductor. Now for the first conductor. For first conductor, what to get there? See here. Here we place the first conductor at distance d from the second conductor. But here, initially here we want to consider through the second conductor I2 amount of current is flow. Then this current at distance d, how much amount of magnetic field is produced? That is the same magnetic field. So that's why at distance d, at distance d, the value of magnetic field, the value of magnetic field due to the current I2 is, what we get there? Due to this current at distance d, how much amount of magnetic field is produced? That is the same, that is B2, which is equal to the, what we get there terms, that is mu 0 I2 upon simply 2 pi d. So this much amount of magnetic field is produced at distance d or at the place of the first conductor due to the current flowing through the second conductor I2. Right? Suppose again this will be the equation number 4. Now we want to find out the force acting on the first conductor. But here, just like this one, here the direction of magnetic field produced by the second conductor is, again here we want to use the right hand rule. So what we get there? Here, see here, if we consider here the outstage thumb, direction of flow of current, then this curl finger indicates the direction of magnetic field. It means that, see here, so this will be the direction of magnetic field. Right? So what we get there? See here. Here the direction is just like this one. Right? It means that here the direction of magnetic field. This arrow represents the direction of magnetic field. It means that at this point the direction of magnetic field is just like this one. Now this will be the B2. This will be the B1 and now this will be the B2. Right? And now this will be the direction of flow of current, that is the I1. Then the force acting on the first conductor by the magnetic field B2 is, what we get there? As per the, again here we want to use the Fleming's left hand rule. What we get there? See here. Here, first of here, this finger, first finger represents the direction of magnetic field, just like this one. This will be the direction of magnetic field. Then middle finger represents the direction of flow of current. Then outstage thumb indicates the direction of force acting on the first conductor. It means that here the direction of force is this one. Right? Now this will be the force is F1. Suppose this will be the force is simply F1. And now this F2 and now this will be the F1. Right? But the magnitude of F1 is, so what we get there? Here, F1 which is equal to, again here we want to use the same equation, that is I, L, B, sin theta. Right? But here current is, what we get there? So the first conductor, how much amount of current is flow? That is I1. Then magnetic field is there, simply B2. And again here, the value of theta is 90. So what we get there? But theta which is equal to the 90, then sin 90 which is equal to the 1. So what to get there? F1 which is equal to the I1L B2. Now we want to substitute the value of B2. So what to get there? So F1 which is equal to the I1 is as it is, L is also as it is, and the value of B2 is simply mu 0 I2 upon 2 pi D. Now we want to rearranging that. So what to get there? F1 which is equal to the mu 0 I1 I2 then L upon simply 2 pi D. Right? So this much amount of force which is acting on the first conductor by the magnetic field B2 produced by the current is I2. Suppose this will be the equation number 5. Right? Now this will be the force acting on the second conductor, and now this will be the force acting on the first conductor. If we see the equation 3 and 5, then what we get there? Here, or from equation 3 and 5, what we get there? The magnitude of F1 and F2 is as it is, F1 which is equal to the F2. Right? But what happened? If you see the direction of F1 is from first conductor toward the second one, and the direction of F2 is from second to first one. It means that their directions are opposite, so that's why here we give the minus sign. Magnitude is same, only their directions are opposite, so that's why what we get there? F1 which is equal to the minus F2, which is equal to the simply there suppose F. Right? So here, if we write this force is F which is equal to the mu 0 I1 I2 L upon simply 2 pi D. This will be the force acting between the two parallel conductors. But suppose here if we transfer this L to this side, so what we get there? F. This F represents the force per unit length of the conductor. So which is equal to the mu 0 I1 I2 upon simply 2 pi D. So this will be the value of force per unit length acting in between the two parallel conductors. Now we want to see the nature of the force. Here the magnitude of both the forces are same, only their directions are opposite. It means that due to this force, this conductor which is moves along this direction, and due to the force F1, first conductor which is moves along this direction. It means that now these two conductors which are parallel to each other, and now that conductors which is moves towards each other. And we know that any body which is moves towards each other, it means that, or it is possible only when if the nature of force is there attractive. It means that when the like current is flow, then at that time the nature of force is attractive. Right? For like current, what we get there? The nature of force is attractive. The nature of force is attractive. Nature of force is attractive. It means that this will be the force of attraction. It is possible only when if the like current is flow.